Hello friends, welcome to my YouTube channel on electromagnetic field theory. In this session we are going to see about wave propagation in a lossy dielectric. Okay, now what is a lossy dielectric? A lossy dielectric is a medium in which the electromagnetic wave as it propagates loses power owing to imperfect dielectric. So a lossy dielectric is otherwise called as partially conducting medium or an imperfect dielectric or an imperfect conductor with sigma not equal to 0. Sigma is nothing but the conductivity. Similarly, what is a lossless dielectric? It is a perfect or a good dielectric with the conductivity is equal to 0. Now let us assume a linear isotropic homogeneous lossy dielectric medium that is charge free. Charge free in sense it is rho v is equal to 0. Now we'll assume all the Maxwell's four equations. So the Maxwell's four equations along with the time factor if we write it is listed as follows. So del dot E is equal to 0 which is Maxwell's first equation, del dot H is equal to 0 Maxwell's second equation, del cross E is equal to minus j omega mu Hz and del cross H is equal to sigma plus j omega epsilon into E. So out of all these four Maxwell's equation, we will try to take the Maxwell's third equation as reference and we will try to take the curl on both sides of equation 3. So when you take a curl on both the sides, we will be getting del cross E is equal to minus of j omega mu del cross H, right? So now we try to implement the vector identity formula. So what is vector identity formula? Del cross A is equal to del of del dot A minus del square A. Now we'll try to implement this vector identity formula to the left hand side of the Maxwell's equation 3. So we will be getting del of del dot E minus of del square E equal to the right hand side remains the same minus j omega mu. Instead of this H we will implement the curl. So we will be getting instead of this H you just not implementing the curl, you just implement the Maxwell's fourth equation. So in the place of del cross H we will implement sigma plus j omega epsilon into E, and therefore since in this equation your del dot E which is in the left hand side the first parameter del dot E is equal to 0 according to Maxwell's first equation, the first term will get vanished and therefore the second term alone remains there. So minus of del square E is equal to the right hand side as it is you will be writing, so minus of j omega mu sigma plus j omega epsilon into E. Now both the sides you have minus, you can eliminate those minus and therefore we can write del square E minus gamma square E is equal to 0, where gamma square is nothing but j omega mu upon sigma plus j omega epsilon. So this term I am considering it as gamma square, right? So this term I am considering it as gamma square. So gamma square is equal to j omega mu sigma plus j omega epsilon. Therefore, this equation becomes del square E minus gamma square E is equal to 0. Now, gamma is nothing but the propagation constant of the medium. So, when you are capable of writing for the E field, we can also write it for the H field. So, for H field, we can write it as del square H minus gamma square H is equal to 0. How do we write for E? So, it is del square E minus gamma square E equal to 0. The same way, del square H minus gamma square H equal to 0. So, now the equations 5 and 6 are called as homogeneous vector, otherwise it is called as Helmholtz equation or it is called as vector wave equation. Now we know that gamma is a complex quantity, so gamma can also be written as alpha plus j beta, where gamma is the propagation constant, alpha is the attenuation constant and beta is the phase constant. So when you take a square term for this, gamma square is equal to alpha plus j beta the whole square you will be getting. So we know that when you square it, you will be getting j square. So j square will be equal to minus 1. Therefore, gamma square is equal to from the equation 5, We know that gamma square is nothing but j omega mu sigma plus j omega epsilon. Now multiply this j omega mu inside the bracket. So you will be getting gamma square is equal to j sigma omega mu minus of omega square j square mu epsilon. So that j square will become minus 1. That's why you got a minus over here. So your gamma square fifth equation has transformed into eighth equation. So gamma square equal to j sigma omega mu minus of omega square mu epsilon. Now we have this seventh equation also we have, which tells you about gamma is equal to alpha plus j beta. Here also we have gamma squared. So we have two equations expressing the gamma value. So we'll try to take the real part of seventh equation and real part of eighth equation. So real part of seventh equation we can get gamma square is equal to alpha square minus beta square, which is equal to compare the real part of seventh equation and eighth equation. In this the real part will be gamma square minus beta square, and in this the real part will be minus of omega square mu epsilon. That is what we did over here. Okay, now if we take the minus sign outside, so minus real part of gamma square will be, here the polarities will change, therefore minus alpha square plus beta square equal to omega square mu epsilon. Therefore rearranging we can write beta square is equal to beta square minus alpha square is equal to omega square mu epsilon. So therefore beta square minus alpha square is again nothing but minus of gamma square. So therefore magnitude of gamma square can be written as square root of omega square mu epsilon the whole square plus alpha square sigma omega mu the whole square, right? Now if we try to solve it, you will be getting magnitude of gamma square is equal to, after taking the common terms outside and solving for the square root, you will be getting omega mu square root of sigma square plus omega square into epsilon square. So here the gamma square is nothing but beta square plus alpha square. So now we have two equations. One is the 12th equations where you have beta square minus alpha square is equal to omega square mu epsilon, and you have a 13th equation beta square plus alpha square is equal to omega mu square root of sigma square plus omega square epsilon square. So we'll take these two equations, that is 12th equation, equation 12 and equation 14 we will take. Now when you solve these two equations, this will get cancelled because one is minus and one is plus, and therefore you will be getting 2 beta square. Therefore you will be getting 2 beta square. The remaining terms are omega square mu epsilon plus omega mu square root of alpha square plus omega square sigma epsilon square. Now you take this 2 to the left hand side. So you will be getting beta square is equal to 1 by 2. The remaining terms remains the same. And then beta, the square root will become in the right hand side, it becomes the square will become in the right hand side as square root. So we will write beta is equal to square root of 1 by 2, the rest of the term as it is we have written, right? Now we'll try to take the common terms outside. So taking the common terms outside and rearranging it, we will be getting omega square root of mu epsilon by 2 1 plus square root of 1 plus sigma square divided by omega square epsilon square the whole to the power of 1 by 2. So here beta is called as the measure of phase shift per unit length in radians per meter and is called as the phase constant or phase number. Similarly, we can also write it for alpha. This is not beta, this is for alpha. So alpha is equal to omega square root of mu epsilon by 2 1 plus sigma square root of 1 plus sigma square divided by omega square epsilon square minus of 1. So where alpha is your attenuation constant or attenuation coefficient, omega is the measure of spatial rate of delay of the wave in the medium, and omega can be measured in radians per meter or it can be measured as nepers per meter. So it can also be measured as decibels per meter or dB per meter. Okay. Now, if you assume that the wave propagates uh, along the positive z axis, so the unit vector will be az, and that es as only the x component, then we can write es is equal to exs of z into ax. This is your 16th equation. Now you substitute the 16th equation in equation 6, therefore you will be getting del square E of z ax minus gamma square E of z ax is equal to 0. So taking out Ex term, which is common in both the two terms, so we will get common term as Ex of z, and the other parameters are del square minus gamma square, which is equal to 0. Now you multiply inside. What will you get? Del square E of z into Ax minus of gamma square E of Az. You will be getting the same, the previous equation. In this previous equation, del square is nothing but you can express it as dou square by dou x square plus dou square by dou y square plus dou square by dou az square. So just we are rewriting this equation and implementing the del square. We will be getting, instead of del square Ex of z, we will be getting dou square E of z by dou x square plus dou square E of z by dou y square plus dou square E of x by dou z square, and this term retains the same minus gamma square E of z equal to 0. Now since E of x, Ex is a function of z only, then dou square x Ex by dou x square and dou square Ex by dou y square will be equal to 0. Therefore, the first two terms will get cancelled, the first two terms will get cancelled, and therefore we will get a term only with respect to the dou z square. So we will be getting dou square Ex of z divided by dou z square equal to minus gamma square Ex of z equal to 0. Now you take in both the terms, you take Ex as common, both the terms Ex as common is there, so you take it as common. The remaining terms are d square by dz square minus gamma square, which is equal to 0. So this equation is called as, the scalar wave equation. This equation is called as scalar wave equation. Now we'll try to see what is a linear homogeneous differential equation with the solution looks like. So Ex of z is equal to E naught e to the power of minus Az plus E naught dash e to the power of plus Az e to the power of j omega t. This is how we'll express the linear homogeneous differential equation. Now here E naught and E naught dash are the constants. So the field must be finite at infinite requires E naught dash is equal to 0, and therefore E naught dash is equal to 0 means, then therefore you mean to say this term e to the power of plus az tends to a wave traveling along minus az, whereas we assume wave propagation along the plus az, and therefore we can have this E naught dash is equal to 0, and therefore inserting the time factor e to the power of j omega 2 in this equation, we will be getting E of z comma t is equal to real part of Ex of z into e to the power of j omega t into ax. Now uh, instead of this e to the power of j omega t, we will be having e to the power of j omega t minus beta z. So therefore E of z of t can be written as E naught e to the power of minus az cos of omega t, expressing this time factor into the cos term, so cos of omega t minus bz into ax unit vector. When you can able to write for electric field, you can also able to write for the magnetic field. So h of z comma t can be written as real part of h naught e to the power of minus az uh, e to the power of j omega t minus beta z into ay unit vector, where your h naught is nothing but E naught divided by eta. So eta is nothing but the intrinsic impedance, complex quantity. It is a complex quantity which is known as the intrinsic impedance. So eta can also be written as square root of j omega mu divided by sigma plus j omega epsilon. So here pi lies between 0 to 45 degree. Therefore, h can be written as h naught. Instead of h naught, we replace with e naught by eta, e to the power of minus a z cos of omega t minus beta z minus pi n into ay, because here eta is equal to square root of mu epsilon divided by 1 plus sigma divided by omega epsilon the whole square to the power of 1 by 4. Here the tan pi is nothing but sigma by omega e, right? So 1 plus sigma by omega e can also be written as tan pi. So therefore this tan pi, this pi lies between the 0 to 45 degree. Therefore h can be written as real part of e naught by eta e to the power of minus az e to the power of j omega t minus beta z into ay in representing the time factor, and this time factor can also be represented in terms of cost term. So h is equal to e naught by eta e to the power of minus az cos of omega t minus beta z minus pi n into ay. So with this we understood the wave equation for the lossy dielectric. Thank you.